Welcome to today's lecture. As we were continuing our discussions on cache memory, today we will focus our attention in how to improve the performance of cache memory. We know that cache memory is used to store your frequently accessed program and data. So, processor during its instruction pipeline requires accessing of cache memory to fetch the instructions, and if it is a load or a store instruction, then it will access for data as well. How fast the cache can respond back is one important parameter which will govern the performance of the pipeline as well. In short, cache memory has a very significant role to play with respect to the performance of any instruction pipeline as well. Today we will focus our attention on a class of techniques known as cache memory optimization techniques. So, we will focus about 6 cache optimizations today, and the idea of an optimization is there are various parameters that impacts the performance of cache. How can you fine tune these parameters such that overall accessing the memory is going to be faster than conventional mechanisms. So, basic cache optimization techniques. Accessing cache memory, we know that cache memory is acting as an interface between your CPU and memory. So, when CPU is there and the main memory is there, we have a high speed device which is called cache memory that is interacting with both CPU as well as your main memory. Now, you can have scenario such that whatever is the requested address is already present in the cache, and that scenario is known as cache hit. We call this time required to perform an access on a cache and return the accessed word is known as hit time. There can be certain cases where the requested address may not be present in the cache memory. We call such kind of scenarios as cache memory misses, and the extra amount of time required to go to the next level of memory, in this case it is the main memory, extra amount of time required to go to the next level of memory, bring a block of data and put it in the cache memory. That is known as miss penalty. So, we have scenario where we are going to have hits in the cache, and the time for accessing a word in the cache and responding back to CPU if it is a hit, it is known as hit time, and the time to respond back with a block of data from an upper level memory to the cache memory, once we identify it is a miss, it is known as miss penalty. The average memory access time for any memory hierarchy consisting of a cache is defined as AMAT, average memory access time, is equal to hit time plus miss rate into miss penalty. Let us see what is the aspect of hit time. When CPU gives an address, it may or may not be present in the cache. Whether it is present in the cache or whether it is not present in the cache, we have to perform an indexing. That means you go into the appropriate index and then perform a tag comparison. Then only we will come to know whether it is a hit or a miss. If it is a hit, we are returning with the requested word. If it is a miss, then the miss penalty starts. You go to the next level of memory, bring a block of data and then you return the word. So, whether or not it is a hit or a miss, hit time will always be there for every memory access. Now, there are certain memory access which may be miss, it may be cache miss. So, the amount of time it is a cache miss, that is called miss rate into the miss penalty, the number of cycles. So, in all the cases there will be hits, in some cases there will be miss, and the miss penalty will be computed in those cases in order to compute average memory access time. What do you mean by hit time? Time to find the block in the cache and return it to the processor. It involves indexing time, tag comparison and transfer of data. Second one is known as miss rate. It is a fraction of time the cache access is resulting in a miss. Number of cache access that resulted in a miss divided by number of access to the cache. Miss penalty is number of additional cycles, it is very important, number of additional cycles required upon encountering a miss to fetch a block from the next level of memory hierarchy. So, these are the three important terms. So, we have to understand that your average memory access time is dependent on how much time it is required to access your first level of cache or your cache memory. So, it's effectively it's the indexing time, the tag comparison time and the transfer time. Second important parameter that governs average memory access time is the miss rate. Lower the miss rate, lower will be the average memory access time. And third parameter is called the miss penalty. Now, how to optimize a cache? Optimization of cache means you have to reduce average memory access time, and average memory access time is defined by this equation of hit time plus miss rate into miss penalty. So, there are three basic motives by which we can reduce the average memory access time. So, the first thing is you try to come up with techniques which will reduce the miss rate, that is called reduction of miss rate. Second technique is try to come up with techniques that can reduce the miss penalty, and the third technique is trying to reduce the hit time. But we have to understand that these three parameters are not independent. If you try to adjust one of these parameters, it will automatically impact the other parameter. So, altogether changing one parameter is not an independent scenario. We may have to adjust, or we may have to see what happens to the other parameters as well. Let us see the first optimization. The first optimization that is done to improve average memory access time is to increase the block size of the underlying cache memory. So, whenever we go for larger block size, we are able to reduce the miss rate. So, miss rate is the parameter which we are going to focus our attention now, miss rate. Now, how this happens? The advantages of going for larger blocks is we are trying to utilize spatial locality. Assume you have a block which consists of 8 words. So, whenever CPU gives an address, you are going and searching in the cache. The moment you come to know it's a miss, you are going into main memory, bringing 8-word block together. So, if there is strict spatial locality for your programs, let's say the access is to the remaining 7 words in the block. Since I bring 8 words together, the subsequent 7 words will always be a hit. Now, if you assume that your block size is doubled, your block can accommodate 16 words. So, once we encounter a miss, 16 more words are brought. That means, if we are going to have sequential access, the remaining 15 of them will be a miss. So, you have one miss and remaining 15 of them will be hit. If we have 32 words in a block, remaining 31 will be hits. So, that means we are able to have more number of hits for one block bringing. But this cannot be made very large. Beyond certain point of time, your programs may not exhibit spatial locality. At this point, larger block sizes are really counterproductive. Second one, this is the point that we addressed just now, is called reduction of miss. And what are these category of miss? These are all compulsory miss. We have seen in our last lecture that there are 3 different types of misses. The first one is called compulsory miss, the misses that are encountered on the very first access of a block. Second one is the capacity miss, which is happening due to smaller cache sizes, and the third one is conflict miss, which happens when 2 addresses are mapping into the same block. Now, how are we able to reduce the compulsory miss in this context? By virtue of the definition of compulsory miss, it's a very first miss that happens on a block. So, when you have a larger block, you are going to miss only at the beginning of a block, and all other subsequent requests are going to be hit. So, when you increase block size, you are able to reduce compulsory miss. Now, I told every parameter fine tuning is automatically going to affect the other parameter. We will see what are the drawbacks of increasing block size. First one, this increases miss penalty. So, how is this point addressed? Consider the case of an example where you have a block, and this block is having, assume 4 words can be accommodated. And the second design is you have a block where you have 8 words. Now, in both these cases, you are having a main memory. Now, to the main memory, we are going to connect using a bus. Let us assume in the case of 4 words, if the carrying capacity of the bus is also 4 words, then in one clock cycle, I can bring 4 words together. Whereas, when I increase my block size to 8, the capacity of the channel that connects the cache memory and the main memory is not changing. So, we require one 4 words will go in single stretch, the next 4 words is going to come in the next clock cycle only, that is the next memory cycle only. So, when you increase the block size with the bandwidth connecting cache and memory unaltered, then more number of memory cycles are required in order to carry this. This will effectively increase the miss penalty. So, miss penalty factor is being governed by the amount of data or instruction that you are or amount of words, the number of words that you are going to bring from the main memory. So, when you increase block size to fill up a block, you require more words. Sometimes there is a restriction in the number of words that you can bring in one stretch due to the limited bandwidth that connects the cache and memory. So, one important disadvantage of having larger block size is increasing of the miss penalty. This means you require more time to fetch a block to the cache. It is basically known as bus width issue, the issue what we discussed now. This will increase conflict misses. So, consider a case that you have some set of blocks that is available with a constant amount of cache memory. So, we will try to work out with the help of an example. Let us assume your cache memory is having 32 blocks and each block is having 4 bytes each. So, you have a cache memory with blocks ranging from 0 to 31. Each is having 4 byte capacity. Now, you increase the block size of this given cache memory. What happens is your number of blocks are reducing to 16, whereas each block is now moving to 8 bytes. So, the entire main memory is being mapped to one among these 15 blocks. If you have a larger block size of 8, or in the previous case your entire main memory was mapped to one among these 31 blocks, where you have one block size is equal to 4. So, since the number of blocks is reducing, that will lead to more conflicts, and such kind of miss is known as conflict miss. And we have more number of blocks will be mapped to the same location. This is what we have seen now. So, just to summarize, when you increase the number of words in a block, or when you increase the block size, then we can reduce compulsory miss, but that will increase the conflict miss, it will increase the miss penalty also. So, there is a point where miss penalty become highly predominant. So, increasing of block size can be done only to a reasonable extent. Sometimes when you increase block size, we may bring useless data and this may evict useful data, that is what is known as pollution. So, you are going to bring more number of words in one shot and these words may not be really used. So, you are trying to bring those words which are not really useful and leading to cache pollution. So, these are the issues associated with larger block size. This is an illustrative picture of the block size plotted on the x axis and the miss rate plotted on the y axis. So, when you increase the block size, you can see that these are all different sizes of cache memory. Let us consider 1K cache, that is the topmost one. The miss rate, when the block size is 16, the miss rate was around 15%, and then it slowly comes down. You can see that there is a downward trend and then the goes high. So, this is an area where you are able to reduce the compulsory miss, but beyond a point, let us say beyond a point, you are going to have an increased conflict miss. The conflict miss is going to be a more predominant one. Now, how can you address the remaining portion? When you have larger cache memory sizes, essentially these are the things, you cannot see much of a change. When you increase the block size, it slightly dips and then it is kept more or less constant. So, this gives us a fair idea about what is the relative trend of block size with respect to miss rate. Second optimization what we are going to study today is about trying to employ larger cache. So, when you have a really small cache and your memory footprint of the program that is running, if it is really big, then your cache cannot accommodate the entire program, leading to more number of misses. But if you have a slightly larger cache, more amount of programs required data and instruction can be kept in this cache. So, larger caches will reduce miss rate. The advantage is we are trying to reduce capacity miss and we can accommodate larger memory footprint programs. But let us see what are the drawbacks. One is longer hit time. When you have larger caches, the number of blocks in the cache will be high. So, once you get the address, to find out the corresponding index, you have to go through a decoder, and that is the time that is known as indexing time. So, when you have larger caches, it means you have larger number of blocks it means it takes more amount of time to index into the cache. And surely when you go for larger cache, it can cost you area and power more. This is a fair comparison chart of considering one particular cache. Let us say this is your 4K cache, this is going to be 16K cache, this is going to be 64K cache, and you can see what is the miss rate. You can see that the miss rate values are coming down from 8.5 to 3.9 to 2.0, and then it still goes down. So this is a fair comparison of block size variation and cache size variation, in what way the miss rate is going to be impacted. These numbers are taken for a particular application. It will slightly vary when you change from one application to another. So this is yet another results that is plotted for the different benchmarks programs, and this different color indicate different benchmark program. When we move from lower cache size to higher cache size, we can see irrespective of benchmark, all the benchmarks are showing a reduction in miss rate. Your miss rate comes down when you move from higher cache size to lower, when you move from lower cache size to higher cache size, and this slightly varies depending on the memory footprint of these programs. Let us move into the third optimization. The third optimization is increasing the associativity to reduce miss rate. Here also our focus is try to reduce miss rate. Fully associative caches are best. Let us try to recall what do you mean by a fully associative cache. Fully associative cache means when you bring a block from the main memory into the cache, then it can be placed in any of the block available inside the cache memory. So in a fully associative cache, block replacement will happen only if the cache memory is full. So even though it is a fully associative cache, whatever you are trying to bring into the cache memory, there is a limit. Fully associative caches are the best, but it will take higher hit time. Why we are taking higher hit time? Because once you give the address, once you divide the address into tag, index and offset, there is no specific case of an index in the case of a fully associative cache, because the block can be kept anywhere in the cache. So tag comparison has to happen across all the blocks, all the available blocks in this cache memory, leading to higher hit time. So what we can do from a direct mapped cache, it is always good to increase the associativity to a reasonable level, because once we move from direct mapped cache to two-way associative cache, then miss rate will come down, but you got to understand that the hit time will slightly increase. When you move from two-way to four-way, again hit time is going to slightly increase. So when you move from 4-way to 16-way to 32-way, we are going closer to fully associative cache. So as we move closer to fully associative caches, or if we increase the associativity, the miss rate will come down. At the same time, the hit time will increase. Since both hit time as well as the miss rate are parameters which govern average memory access time, finding an optimal balance is a design challenge. The advantages is we are trying to reduce conflict miss. When you have direct mapped cache, there will be two blocks mapping into the same set. When you go for two-way associative, even though these two are mapping into the same set, still we can accommodate them because my one set has two blocks. It will reduce the miss rate and it is trying to reduce the eviction rate. And what are the drawbacks? Once you move to higher associativity, it will increase hit time, and it's slightly complex design because you have to perform parallel tag matching and then the word selection, and you will take more time to search in the set because tag comparison time is slightly more. Now this is a case where when you are having a direct mapped cache, then your entire main memory, for example, you assume you have a cache memory with 4 blocks, entire main memory has to be blocked to one among these 4. When you are going for a two-way associative cache, then what we do is these 4 blocks are reorganized into index 0 and index 1. So you are trying to keep your data anywhere in way 0 or way 1 of the same index. So this gives you less amount of eviction and reduction in conflict misses. Let us try to see, this is an example that is taken from the SPEC 2000 programs, one of the representative programs. We are trying to increase the cache size, and on the y-axis we are having the miss rate, and you assume the red color one is direct mapped cache, we can see that when the cache is very small, whatever miss you are going to have, the miss is going to be very high. That is typically what is known as capacity miss. Once we increase the cache size, misses will slowly come down. That means your capacity misses will reduce, and then you have something called conflict miss in this region, and then at the end you have something called compulsory miss. So compulsory miss means even if it is an infinitely large cache, still you encounter compulsory miss. So compulsory miss cannot be reduced. You can see that when you increase the block size, then this whole of your compulsory misses are still there, but when it comes to conflict misses, the amount of conflict miss is drastically reduced. So it's always better to go for a fully associative cache, but this shows that for a fully associative cache, we have drawbacks pertaining to the hit time. So we can finally balance somewhere between direct mapped cache and a fully associative cache. So this particular graph gives us an intuition that initially it will be the capacity misses that dominates. Once you increase the cache size and once you are going to slowly have your miss rates coming down, but some of your misses, so always your total number of miss, few will be due to capacity miss, few will be due to conflict miss, and few will be due to compulsory miss. Compulsory miss you cannot reduce at any point of time beyond a point, and in the case of conflict miss you can reduce if you increase the associativity from direct to 2-way, 4-way or 8-way. Yet another optimization technique is known as multi-level caches. So we have seen 3 techniques which will reduce miss rate. First one is using larger block size, which will reduce compulsory misses. Second one is using larger cache size, which will reduce capacity misses. Third one is using higher associativity, which will reduce conflict misses. Now the next aspect is we are going to focus our attention to another parameter in the average memory access time equation, and this parameter is the next parameter that is not at explode, that is the miss penalty. Now how will you get this? Multi-level caches are going to reduce miss penalty. So performance gap between processors and memory is widening. So we have seen that our first level cache should be small and simple. It should be like 2-way or 4-way associative, it should be small, many parameters we have seen, but if you keep it small, then compulsory misses is going to be constant, but your capacity misses are high, and when you make it slightly large, then hit time will increase. So we have to design your cache memory in a hierarchy. Caches should be faster to keep pace with the speed of processors, and caches should be larger to overcome the widening gap between the processor and the main memory. You can add another level of cache between the cache and the memory, and that is known as your L2 cache. The first level of cache, that is L1, can be small enough to match the clock cycle time of the very fast processor, means lower hit time. Second level cache can be large enough to capture many accesses that would go to main memory otherwise, thereby lessening the effective miss penalty. So our idea of keeping L1 cache simple is to reduce hit time. Our idea of keeping L2 cache large enough is to reduce the miss penalty. This is the idea. You have a CPU, and then you have your first level cache, your second level cache and third level cache. As we move from CPU into the main memory, as we move from cache hierarchy, when you move from level 1 to level 2, cache size will be larger. So effectively the access time, that is T2 is the access time, T2 will be larger than T1, whereas T3 is going to be larger than T2, and Tm is the access time of main memory. So when you move from CPU side to main memory, we are going to deal with larger memories leading to larger access time. And since the capacity of the memory is relatively large, we could reduce the capacity miss, so miss rate will come down. Now Hx is going to be the hit level of a particular level of cache, and Tx is the access time of level x in the cache hierarchy. So average memory access time is hit time of L1 plus miss rate of L1 into miss penalty of L1. This is our standard equation. Now miss penalty of L1 can be defined as hit time of L2 plus miss rate of L2 into miss penalty of L2. You substitute this, you will get the remaining values. So in our previous approach, we have found that average memory access time is hit time plus miss rate into miss penalty. Miss penalty itself is going to be the access time of next level of cache into miss rate of that cache into miss penalty of the second level cache. Multi-level caches are, we have seen that it is reduced miss penalty. There are two terms that we would like to draw your attention to. The first one is known as local miss rate. It's the number of misses in a cache level divided by the number of memory access to this level. The second one is called global miss rate. It's the number of misses in a cache level divided by the number of memory access generated by the CPU. Here is the question. Consider the case you have an L1 cache and then you have an L2 cache. Now you assume you are getting 100 requests to the L1 cache, out of which let us say 80 is going to come to get a hit. So it is 80 divided by 100, that is 0.8 is the miss rate of L1. So when I redefine the local miss rate, it is a number of misses in a cache level, that is 80 divided by number of memory access to this level. So it is 80 divided by 100, it is 0.8. Now out of this 20 that misses, 20 only is going there. Now in this 20, you assume 5 of them are missing. So what is the miss rate of L2 cache? 5 are missed out of 20, that is 0.25, that is a miss rate. So the local miss rate of L2 is 0.25. What is the global miss rate? It is the number of misses I encountered. I have encountered only 5 misses. What is the total number of memory requests? It is 100. So that will give you 0.05. So in this example, the local miss rate of L1 cache is 80 divided by 100 because I have, so local miss rate. So this is whatever I have covered is the hit rate, and you have to find out the misses. So in this case, the misses are going to be, the number of misses that I get here is, this is 20, so it's 0.2, whereas in this case, we now wanted to introduce two important miss rate parameters. The first parameter is the local miss rate and the second parameter is the global miss rate. Local miss rate is defined as the number of misses in the cache level divided by the number of memory access to this level, whereas global miss rate is defined as the number of misses in the cache level divided by the number of memory access generated by the CPU. There are two different types of miss rate that we wanted to introduce. We will take a small illustrative example to understand this concept. Consider we have two caches, L1 and L2. So this is your L1 cache and this is your L2 cache. Assume CPU is going to give you 100 cache access, out of which 20 is missed in L1. So its number of misses is 20 and number of cache access is 100. So number of misses in the cache level divided by number of memory access into this level, that is the local miss rate. So the local miss rate is 0.2. That means when I have 100 access coming to L1, out of which 20 is missing, 20 divided by 100, that 0.2 is the local miss rate. Now these 20 are actually going to L2. Now assume that out of the 20 that reaches L2, you are going to have 5 of them missing L2. So number of misses in L2 is 5, number of access to L2 is 20, so leading to 0.25 as the local miss rate of L2. So the local miss rate of L1 and L2 is defined by the number of access coming into that particular level and the number of misses that you encounter in that particular level. Now global miss rate of L2 means I am missing 5 in L2 from among 100 accesses that CPU has given, leading to my global miss rate of 0.05. So global miss rate and local miss rate are both needed in order to appreciate what is the significant improvement we get from multi-level caches. Now we have something called inclusive and exclusive caches. So cache memory itself, by virtue of the organization, we are dividing them into inclusive and exclusive caches. So inclusive cache means multiple hierarchy is actually a subset. So when you have a cache architecture in which your L1 cache is a subset of L2, then we call it as an inclusive cache. If we have L1 and L2 both are mutually exclusive, that means there is nothing in common in L1 and L2, we call it as an exclusive cache. So, as a summary, I am going to repeat once again, inclusive cache means a subset of L2 is taken to L1. So, whatever is there in L1, it will surely be there in L2 also. Exclusive cache means whatever is there in L1, it will never be there in L2. This means the effective cache memory size, if it is an exclusive cache, will be more, because the size of L1 plus size of L2 is the effective cache size. Whereas in this case of an inclusive cache, the effective cache size is equal to the size of L2, because L1 size is actually taken away from L2. This is yet another way of looking at an inclusive cache hierarchy. Whenever we get a core request, the request is going into L1, and then whenever it is missed, you can go into the L2, that is called the last level cache. And whenever a block is to be evicted, then you are evicting from L1 into L2. L1 is actually a subset of last level cache. But when in this case, whenever there is a request, the request is directly going to come from memory, rather than filling up in last level cache, it is directly going and filling in first level cache. Evictions happen from there into that. So, L1 is not in last level cache, that is called an exclusive cache hierarchy. Next optimization is yet another way to reduce miss penalty is to give priority to read misses over writes. Consider a scenario, if a read miss has to evict a dirty memory block, the normal sequence is write the dirty block to memory and then read the miss block. Consider the case, these are all RISC MIPS instruction. Store word R3 512 of R0, that means content of register R3 is going to be stored into memory, say location 512. Then I have to load a value from memory location 1024 into R1, and then yet another is I am loading one more value from again this memory location. So, now the peculiarity is when you perform the split up of the blocks, the first one has to perform a write on location 512, or essentially it is a block 512. The second instruction will perform a read on location 1024, and the third one is again read on location 512. In this case, it is basically a conflict that is going to work here. So, you are going to have a write operation, we are going to write something into block 512. After that, we are going to read a location. Now, once this write going to happen in memory, in the meantime, I wanted to have a read, assume that this read is a miss. Once the read is a miss, you are supposed to bring the block. But when the write is happening into the same block in which the read is going to be performed, then it is always better to prioritize this read over write. If a read miss has to evict a dirty memory block, the normal sequence is write the dirty block first. We are going to complete the write and then we are going to read. The optimization can be, first you copy the dirty block to a buffer, then you read from the memory and then write the block, thereby your write operation will be slightly delayed and your read operation is being prioritized over the writes, such that you can improve the performance. In write through caches, write buffers hold the updated value of the block, and when you encounter with a read miss, you have to read from these write buffers as well. What do you mean by write through cache? We have seen in our last lecture, caches are divided into two based upon where writes updates are happening. If it is a write through cache, then any writing on cache memory, it is reflected in main memory as well at the same time, such that cache memory and main memory are coherent. When you are using write back cache, all the writes happen on the first level cache only. Only when there is an eviction from the first level cache, then only the updated writes goes to the next level of memory. So, when you have a write through cache, This every write that happens on cache memory has to happen along in main memory also. Processor need not wait until the main memory write is over. So cache, whatever value that is written in cache, a copy is kept in a buffer known as write buffer, which will parallelly write it into main memory. So processor will continue its task by putting the appropriate data to be written in the write buffer. As and when the queue is serviced, the contents will be updated in the main memory. So when you encounter a read miss, then rather than directly going to main memory, sometimes the value might have just written and the block is evicted, it may be present in the write buffer. So searching in write buffer sometimes will help. Either wait till write buffer is empty or search in the write buffer before going to the memory. Now we will see the sixth optimization for the day. Avoid address translation for indexing. We know that CPU is giving you virtual address, and this virtual address has to be converted into physical address before accessing the data from the cache. Now what do you mean by physical address? Physical address means it is the address of the location when it is present inside main memory. But when CPU is giving a virtual address, you have to convert it into physical address, and that translation is done with the help of main memory management unit and translation look-aside buffer. So you have page tables that converts your virtual pages into physical frames, and then using offset. These are the concepts typically we learn in operating systems course. So virtual address to physical address has to be done before cache lookup. Now we know that once you access cache, there are two operations that is involved. First, you have to index into the corresponding set. Once you index into the set, the tag value which is stored in the set is extracted and it is compared with the incoming tag in the address. So indexing happens first, followed by tag comparison. So if the indexing can be done only if you get the physical address, then before going to indexing, first step should have been converting from virtual address to physical address. That is, when CPU gives an address, the virtual address, first stage is using a memory management unit or a translation look-aside buffer, convert the virtual address into the physical address. And once you get the physical address, then divide into tag, index and offset. Using the index bits, go and refer into the location, and then you perform tag comparison. Since there is a translation time that is involved, accessing cache is going to be very slow, and if it is an L1 cache, then your instruction pipeline also has to be stalled. The optimization idea is, since your indexing is happening not with the most significant bits, let's say if the virtual address portion or the physical address portion, if the index bit is remaining unaffected, then index using virtual address. Start indexing with the virtual address. In the meantime, do the address translation and get the physical address and the tag. So your tag portion is inside the physical address, whereas your indexing will be part of the virtual address bits. So the role of TLB access is actually in the critical path. So the idea of this optimization is indexing by virtual address and tagging by physical address. This is known as virtually indexed, physically tagged cache. So we would like to give an illustrative exercise here. Consider the case that CPU is going to give us a virtual address that consists of 12 bits of offset and 20 bits of page number. So what happens is, this is going to be converted into say 10 bits of physical frame, so and 12 bits of offset. So this translation from 20-bit page number into 10-bit frame number, this is taken care of by your page table or TLB. So this is your physical address, and only if you get the physical address, then only you can divide into tag, index and offset. This optimization principle is saying that if your index and offset is within this 12 bits, if your index and offset values are within this 12 bits, then the index bits are not dependent whether it is a virtual address or a physical address. That means you will be indexing using the virtual address portion, and only if you get these 10 bits, then only your tag bits can be identified. So, these are basically known as virtually indexed and physically tagged caches. This will help us such that prior to translation we are able to go into the cache memory by indexing, so that you got into the appropriate set. In the meantime, translation happens, you get the physical address. Once you get the physical address, the most significant portion of the physical address is the tag. You have the tag ready. Virtually indexing, extracting the tag, comparison of the tag, and the tag is part of the physical address. And this is a classical case study in which we are talking about a 64-bit virtual address which is divided into 50-bit page number and 14-bit offset. That is why we are telling 4 KB, 16 KB page size. 16 KB means 2 power 14, so 14 bits are used for that. Now, you are going to search in your TLB in order to get the physical address. So, once you get the physical address, is 64-bit is converted to a 40-bit physical address, out of which 14 are offset and remaining 26 is the frame number. Now, this contains your tag bits, your index bit and the offset bit. So, if the indexing can be done within this, then it is possible for us that directly with the offset value that is available, I could easily access cache. So, the idea of avoiding address translation is, if the cache memory can be designed in such a way that the index bits comes perfectly under the page offset, such that indexing can be done prior to address translation. But anyway, tag cannot be done prior to address translation, because tag bits are typically the most significant bits of your address, and most significant bits will be different in the case of a virtual address and the physical address. So, we have just completed 6 different optimizations for the day. We tried with 3 optimizations, 3 focusing on reduction of miss rate by having larger blocks, larger caches and higher associativity. Then we learned 2 techniques to reduce the miss penalty. The first technique is having multi-level caches, wherein L1 cache is kept small and simple enough to have better hit time, and L2 caches are kept wide enough such that you could reduce L2 miss rate. Then the other technique is prioritizing read misses over writes, and the last technique is trying to reduce hit time by avoiding address translation. Few tutorial problem sheets are being uploaded. So, next lecture we will be having a short discussion about how to work with numerical exercises pertaining to the design and optimizations of cache memory. So, with this we will complete today's lecture, and thank you very much.